6, the electronic structure of atoms. This is where it gets fun. Now, when we look at the periodic table, then what we're going to see is filling orders, okay? So when we look at the periodic table, we're going to fill the s orbitals over here in the first section, group 1 and group 2, okay? We're going to fill at the n level. Now, S and P are the representative elements, and they go together because they're going to fill the p orbitals, and they're going to be in the same exact level. So N and L, S and P fill in the exact same level. So if you look at the periodic table, then you have lithium is 2 and boron is 2. Lithium is 2s, boron is 2p. Now, once you get into the Ds, that's the transition metals. That's the d orbitals in this section here. And you're going to fill one level below. And so when we fill, because of the energy levels, you're going to have a delay. So, for example, if you look at scandium, which is number 21, it fills after calcium. Well, if you look at the energy levels and you just run down the numbers, so 1, 2, 3, 4, 5, because N just goes down the periodic table here. All right, so when you fill for calcium, it's 4. So I'm going to try to write this in. It's kind of fun here. This is calcium. So calcium is at 4s. Then you're at scandium, which is 3d, because the D's fill one below. So that happens all the time. So yttrium, strontium is in the 4s's, but yttrium is in the 3d's. No, the 5s. 1, 2, 3, 4, 5. See, I can't do. So scandium would be, strontium would be 5s. Can't do here. And yttrium would be 4d. So going back after that, if you look at the periodic table, calcium is 4s, scandium is 3d, strontium is 5s, and yttrium is 4d. So they fill that way. Now, if you go down to the lanthanide, actinide series or intertransition metals, what you'll see there is those are the f orbitals. And actually, they're going to fill 2 below. So if you look at them, they're called the lanthanide and the actinide series. So you get barium here. You get radon here. And this is where it actually gets weird, because if you look, you got lanthanum and you got actinide, and then this group then falls in here, because if you'll notice the numbering, there's a gap between lanthanum. Lanthanum is 57, hafnium is 72. So all of the numbers come in here. Cerium, which is 58, etc. Thorium, which is 90. So what actually happens is, and this is where the weird wonky gets, is if you look here, barium is 1, 2, 3, 4, 5, 6. Okay, so barium is 6s. Lanthanum is 5d. And then cerium is 4f. So radon, and let me change colors on this so it really differentiates. Radon would be 7s. Actinide is 6d. And thorium will be 5f. So it's kind of weird. Okay, it's really weird. All right. The D's start filling at the 3rd energy level. So they start at 3. The F's actually start at 4, but the 4 doesn't come in until after the 6. No, that's something's not right there. So, wait. Barium has to be 1, 2, 3, 4, 5, 6. No, it's 6. So that's 5D. So that would be 4F. Yep. So, yeah. All right. So, I did it right. Love this confusion here. So we have 4F, 5D, 5D there, and then here we've got this partnership here. So I actually did that right. So the F start at the 4th energy level, the D start at the 3rd energy level, and if you'll notice, the P's start at the 2nd energy level, and of course the S's start at 1. So you have one S and one S1 and one S2, because that's hydrogen and helium. And that's, you know, if you put the hydrogen and the helium here, this starts at 1. Okay, now this is this is way easier in person, but I'm hoping that this makes sense if you sit and watch it a couple times. And it makes life is a whole lot easier as we work problems. So this is out of your periodic table. They're saying the same thing, that I'm the M, the S, D's, P's, and F's. And remember, these are in, they match. This is n minus 1, and this is n minus 2. Okay, so here's your periodic table, and this is in the text, and these have the actual. Now, be careful about actual, because there's some tricks that occur in real atoms that you're not necessarily responsible for. But we'll go through, we're going to go with the keep it simple approach. So as we work problems, we're going to try to keep it simple. Now, let's go back and think of how these numbers are applying to the quantum numbers. So the question says, is there a 3p shell in the hydrogen atom? And the answer is no. And the answer is no for 3f's, because the hydrogen is in the 1st energy level. So the only thing the 1st energy level has is an S, because n is equal to 1, so L has got to be equal to 0. Because a P is L is equal to 1, and an F is L is equal to 2. No, 3. 3. Doesn't matter. We cannot go beyond L is equal to 0. Okay? Now, these are some of my favorite problems here, is determine which of the following sets of quantum numbers is possible and correct any that are incorrect. And again, we're going with the rules of n. L is equal to 0 up to n minus 1. M sub L is negative L through to 0 through to plus L, and M sub S is plus or minus 1/2. So that's all you have to keep in mind. And no, you don't get those rules on the periodic table or anywhere else. So if n is equal to 3, can L be equal to 2? Yep. If L is equal to 2, can M sub L be equal to? Yep. And can M sub L be equal to minus 1/2? Yes. So this one is correct. So we're good on that one. So on B, n is equal to 4. Can L be equal to 3? Nope. So let's pick the maximum it can be. You could pick any of the other ones, but we'll go with 3. If L is equal to 3, can M sub L be equal to minus 2? Yes, because if L is equal to 3, M sub L can be equal to minus 3, minus 2, minus 1, 0, 1, 2, 3. As long as it's one of those values, we're okay. And can an M sub S be equal to 1/2? Yes. So at this point in time, we've corrected the whole thing. All right. So if n is equal to 2, can L be equal to minus 1? No, because L can never be minus 1. So let's correct that to plus 1. So if L is plus 1, can M sub L be equal to 0? Yep. Can M sub S be equal to minus 1/2? Yes. So if n is equal to 5, can L be equal to 3? Yes, because it can be 0, 1, 2, 3, or 4. And M sub L, if L is 3, can be minus 3. Now, if else was 2, which is allowed by N, M sub L could not be minus 3 because it can't exceed. So we're okay on that one. And then we have M sub S is equal to plus 1/4. No, we could go with plus a half or minus a half. It doesn't matter, and we're good to go. So basically, in these, and you're most likely to see this in the multiple choice format, which of these would be possible or which one would not be possible. So watch for possible versus not possible. Okay, so we're going to write the electron configurations for these species right here. And in order to do this, there's a couple tricks. First off, we're going to start with some boxes. And the boxes show you what each orbital looks like. You're not allowed to use boxes on the exam. You will not have boxes on the exam. Okay? Not happening. But to get you started, we're going to use the boxes. Okay? So I've got 2 boxes per page, and there are extra boxes that you can copy. And after the first couple, I'm going to end up adding pages as we go. So, for example, I've already added a page right there. So, the boxes are nice, but they're a crutch. But you do need a periodic table. You cannot do this without a periodic table. So, first thing we've got is oxygen. Well, let's look at the periodic table. Oxygen has an atomic number of 8. That means it has 8 electrons. Okay, so it has 8 electrons. It has 8 protons, 8 electrons. So when we go to put them in, basically we have to account for every electron starting at hydrogen. Think of these as steps. You have to hit each step on the way. So we're going to have to hit 8 steps. So we'll put 1 in 1s, then we'll pair it. Remember, we can't finish a set or move on to the next one until we finish the set. So that's 1, 2, 3, 4. And notice I'm pairing my spins. It doesn't matter if you start up or start down. And I'm using half arrows just because I'm lazy and there's you to write. Okay, so 1, 2, 3, 4. Hund's rule, 5, 6, 7. Remember, we singly pair until we do 8. So, the boxes are nice, but they're bulky. So what we want to do is write this in complete notation. And the net effect is we're going to take the boxes and convert them to the SPDF standing. So we have the 1s orbital with 2 electrons in it. We have the 2s orbital with 2 electrons in it. We have the 2p orbital with how many electrons in it? 4. Now, if you take a second, 2 plus 2 is 4 plus 4 is 8. So at 8, that's how many we have, that's how many we wanted. Now, I'm going to show you what the shorthand is. Now, for elements between 1 and 18, shorthand is pretty much kind of useless. But when you get up beyond that, and we're going to do some of those, you're going to see that you really like the shorthand. Now, on the exam, you are going to be using both. So you need to know how to do both. So the shorthand actually qualifies as, if you look at the periodic table, a filled shell is the noble gas. And so, for example, when you look at this, this is your filled shell. So it corresponds to the noble gas, which is helium. So 2s2, 2p4 would be your shorthand. Now, again, you're looking at that going, that didn't really save me anything. No, it didn't. But if we're doing anything like yttrium, cobalt, way down, americium, in the inner transition elements, you're going to go, please let me use that shorthand notation. Okay, now, you're like, wait, but there's another box. I'm going to change colors again because I want to do the charged species as we go. So, if oxygen has 8 electrons, oxygen 2- has 10 electrons. So when we put those in, 1, 2, 3, 4, 5, 6, 7, 8. Okay, that's our oxygen. Now notice that we're going to finish filling that shell. So we have 1s2, 2s2, and now we have completed the P shell. So if you look at oxygen on the periodic table, what we've done is we've had 2 electrons. So we've actually gone to neon. So at this point, we are a closed shell. So our shorthand for this is neon. Remember back when we started oxidation numbers, I told you that there was a method to the madness? Well, here's the method. The method is the goal for each species is to have a complete shell. So oxygen is short 2 electrons. So it's going to gain them to go to complete shell. Sodium, on the other hand, is one past that complete shell, so it wants to lose them to go back to the shell. That's why the nonmetals tend to be negative, because it takes they gain less electrons to complete the shell. Whereas the metals, it's easier to lose theirs to go back to complete shell. Okay, does that make sense? All right, so we're going to do this again, except this time we're going to do aluminum. And we're not going to use the boxes. So if you look at aluminum, aluminum has an atomic number of 13. So it has 13 electrons. So we're going to follow it through. So we're going to start with hydrogen and helium. That's 1s2. Because that's 2 electrons. That's the hydrogen and the helium. And then we're going to do lithium and beryllium, which is 2s2. We're going to do boron through neon, which is 2p6. And then we're going to do sodium and magnesium, which is 3s2. And then we get to aluminum, which is 3p1. Now, as a double check, 2 plus 2 is 4, plus 6 is 10, plus 2 is 12, plus 1 is 13. So we have 13 electrons. Yay! And if we look at it, so in this particular case, all of these are closed. So they become neon, and we have 3s2, 3p1. Now, if you're looking at it going, wait, how do I count electrons? Well, this is easy. Neon is 10. 10 plus 3 is 13. So while we're doing this, let's go ahead and do aluminium 3 plus. Well, if we look at the aluminum 3 plus, which 3 electrons are we going to lose? We're going to lose the outermost. So we're going to lose these 3. So for aluminum 3 plus, we're down to 10 electrons. So there are a couple ways to write this. You could write it as a simple neon core, or you could write it as 1s2, 2s2, 2p6. Both of those are equally accurate. One's shorthand, one's not. Therefore, we're good to go. So we just did those. Now, we're going to take this a step farther, and we're going to move back in color to, let's do zinc. Zinc has an atomic number of 30. That means it has 30 electrons. Okay, so if we have 30 electrons with our boxes, 1, 2, 3, 4, 5, 6, 7. Notice as I do these, I'm obeying the Hund's rule. 7, 8, 9, 10, 11, 12. Okay, 13, 14, 15, Hund's rule, 16, 17, 18, 19, 20. We're back to Hund's rule because now we're in the D's, which are degenerate. Remember, P's are degenerate, and D's are degenerate, and F's are degenerate. And those are the ones where you have to obey Hund's rule. 2, 4, 10, 12, 14, 16, 18, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, and 30. Woo! Now the box is good. So we have a 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and 3d10. Okay, again with the counting, 2 plus 2 is 4, plus 6 is 10, plus another 10 is 20, plus another 10 is 30. Woo! We're good. Now, looking at zinc in the periodic table, we want the nearest closed shell. And that's going to be these species right here, and that's going to be argon. So we would write this as argon 4s2 3d10. So there's our zinc. Okay, now that begs the question, what are we going to do when zinc is 2 plus? Now, if you remember way back, we did oxidation numbers. There were 3 that I told you that were monovalent that you had to know. They were zinc, cadmium, and silver. I'll explain silver in a minute. We said that we're going to lose the outermost electrons. Well, technically, the 3D is part of the third energy level. It doesn't fill until later, so you can't put it in the core. But this is a filled inner subshell. So that means don't touch it. So the only electrons that can be lost, you can lose only the 4s. Now, let me explain about the s's. The s's are the outermost electrons, okay? It's kind of like sticking your hand out of a car at the Runaway Mine Train in Dahlonega at Six Flags. Runaway Mine Train. There's this pole there. Everybody's just like, I want to reach out. Don't do that. Don't reach out and try to touch that sucker, because you're moving at a really fast clip, and you stick your hand out, that pole's going to take it off. So basically what I use is the S's are expendable. And if anybody watches the old Star Trek, not the new ones, not the Star Trek Next Generation, I'm talking about the old William Shatner, goofy, low-key budget. They're kind of fun to watch. Okay, I call the S's the red shirts, because if you notice, when they go into the transporter, go down to the planet, whatever planet it is, pick a planet, the red shirts never come back. They're cannon fodder. They're the ones that are gone. So you can always, doesn't matter what else you lose, you can always lose S's. So what happens is when you actually fill this back up, and yes, I'm still obeying Hun's rule as I do this, and you're like, well, it's faster if you don't. Yes, it is. But it's one of those ingrained things. Okay, so if we look at it, these are the ones we're going to lose. So we don't have those anymore. So our complete now would be 1s2, 2s2, 2p6, 3s2, 3p6, and then 3d10. Well, if zinc is 2 plus, that means it has 28 electrons. So 2, 4, 10, 10, 28. So that's 28 electrons. So the shorthand is still the argon core, because this is the argon core now, but we have the 3d10. Now, some people, and this is fine if you do this, like to write it like this so that you see, look, the S's are gone. Because of the way this works, most likely these are going to be multiple choice. ID, multi-select. If you haven't figured it out, I like multi-select. And there's usually more than one answer. So either is fine. And you may see that. So again, we're counting electrons. So again, as we move up in electrons, the boxes may be convenient, but they're kind of annoying. Okay, so let me add another empty box so that I can move on to my other species. I did zinc, and I did zinc 2 plus. I want to do ruthenium, and I want to do americum. All right, ruthenium is a transition metal, and americum is an inner transition metal, and while I happen to be looking at it, This one is 95. Yeah, it's 95. Curium is 96. And ruthenium is 44. Alright, so we're going to do the long way and then we'll do the short way. So the ruthenium has 44 electrons, which means we have to start at hydrogen and move through. So 1s2, 2s2, 2p6. That takes us all the way through neon. Then we'll start the 3s row, 3p6. That takes us to argon. We got to go through 4s2, 3d10. That takes us through zinc. Back to the 4p6. That takes us to krypton. And ruthenium is in the next row, so it's 1, 2, 3, 4, 5. I always have to keep counting. 5s2. And then we go down to the 4 Ds. How many Ds? 1, 2, 3, 4, 5, 6. So 6 Ds. So quick double check. We have 10, 12, 18, 20, 36, 38, 44. So we have 44 electrons. So shorthand, and shorthand is way better for this one. You look at ruthenium, and it's in the 5th energy level, well, 5th row. That means that you go to the 4th row, close, so that's krypton. And so everything from here to here is krypton. This is krypton. So it's 5s2, 4d6. Now, if I still want to double check the numbers, krypton has 36 electrons, plus 2 is 38, plus 6 is 44. So we're still good. All right. Now, americium, wow, that's 95. So I'm going to look at this sucker. Okay, that's in the actinide series, so we're going to have to go all the way through. So I'm going to do the shorthand, the longhand notation, and then I'll do the shorthand. So it's 1s2, 2s2, 2p6. That takes us through neon. The 1s2 takes us to helium. Then it's 3s2, 3p6. That gets us to argon. Then it's 4s2, 3d10, 4p6. That gets us to krypton. Then it is 5s2, 4d10, 5p6. So that gives us to xenon. 1, 2, 3, 4, 5, 6. So then we start our 6s2. We do 5d1. 4f14, and then we come back to the D's. Now, I don't care whether you do the D's first or the D's second, but don't have two sets of D's. It actually would go 5d1, 4f14, and then it goes back to 5d9, but that's annoying. So combine your D's if you need to. If you don't, then don't, if you only have one. But otherwise, combine them. So we're at 5d10, 4f14. I lost my mind. Okay, so we're back to 6p6. That should take us through to 1, 2, 3, 4, 5, 6 radon. Okay, then we're at 7s2, 6d1. And then that's actinide. And then we're going to go 1, 2, 3, 4, 5, 6. So then we'll have 4f6. Wow. Okay, so, I'm going to go back and count it every time because I'm so OCD about that. 4 and 4 is 10, 36, 38, 48. I'm going to skip 50, 56, 66, 70, 80, 86, 88, 89, and 6 is 95. Whew! So I made it. Alright, so let's do the shorthand for that critter. So we're at radon, americium, where are we? Okay, so that means that radon would be our core. Now, the radon core is going to stop right here. This is our radon core right there. So then we would have 7s1, 6d1, 4f6. Okay, so if you just started with if you were not asked to do the long, you could do the core. And remember, that's 86, and 1 is 87, 88 plus, wait, so I lost something. Hold on. Oh, see, I just counted to 94, and I'm like, that's not right. I can't throw away an S just on a whim. Okay, so there we go there. Now, one thing I didn't explain or tell you about, and I'll go ahead and use Americum here because I've just got it drawn. So you may see this. Okay, if you see this, this means that this is in the excited state. And what you do is you take one of the outermost electrons, I prefer the most, and you move it up. So we would still have the radon core, and I could take the 7s, 7s electron, and move it up to 8s1. Or I could have done the radon core, 7s1, 6d2, 4f6. Or I could have done the radon core, 7s1, 4d, whoops, helps if I don't change the number, right? Keep your numbering, 6d1, 4f7. Okay, so what we do with the excited state is we move an electron to a higher energy. We cannot lose it, because if we lose it, it's an ion. But if you still count it in there, so with the radon core we have 86, 87, 88, 89, 95. So in all of these we maintain the number of electrons, we just pop it up. And you may be asked to determine an excited one. Okay, so now that we know the basics, let's look and see what we can do with the electron configurations here. Alright, so what I've done is I've paired these. You can see it with barium. We have the pair here. And so arsenic, if we look at arsenic, arsenic is number 33. So it's going to have an argon core. And it's 1, 2, 3, 4 S2, 3D10, 4P, 1, 2, 3. Okay? So, if we move from an argon core to a krypton core, what did we do? We had to add 3 electrons. So that means our ion that we're dealing with is 3 minus. Hard part, electrons are negative. Okay? So barium here, well, what's barium? And we can use the core. I certainly want to do it there. It's xenon. 1, 2, 3, 4, 5, 6. And yes, I am counting layers as I go down. I do this all the time. So if we're going to lose 2 electrons, we cannot lose anything in the core. Cannot lose anything on the xenon. So we're going to have to lose those 2 S's. So that means that we have barium 2+ has a xenon core. Phosphorus is 1s2, 2s2, 2p6, 3s2, 3p3. It's above arsenic. And we could have used the core with that one, and that's fine. We can use it. So in this case, we're going from here, and we're going to gain 3 electrons. So that means that we can go to the argon core. Now, we also could have written it as 1s2, 2s2, 2p6, 3s2, 3p6. Doesn't matter which one. They're interchangeable. Okay, and this one says, wait a minute, we have an argon core, and we're going to add 1 electron. So argon is 18, so 1 electron is 19, so this should be potassium. And if you're in doubt, the easiest way is 18 plus 1 is 19. Hey, it's potassium. So notice we've lost the 1 there, so we're going to have potassium 1 plus. Now we come to 10. 10 is a krypton core. So 1, 2, 3, 4, 5. So it'd be 5s2, 4d10, 5p2. So then the question is what is 10 2 plus? Well, this is where it kind of gets fun. So we could either lose, and let me highlight, we can lose either this one or this one. So we have the krypton core, 4d10, 5p2, or we have the krypton core, 5s2, 4d10. In this particular case, we could lose either one, which brings us to, what's the other charge for tin and lead? They're either 4 plus or 2 plus. So you get the krypton core, 4d10, by losing both the s's and the p's. Now, do you have to write the 4d10? Well, look at it. Krypton is 36, and 10 is 46. And if you lost 4 electrons, then that would be 50. If you leave off the 4d10, then you have krypton, which is 36, plus 4, which is 40, which gives you zirconium, which is not the same thing at all. So the answer, the long answer, is yes. All right, so over here we have krypton. So we're going to go to krypton, and then we're going to go 5s2, that's strontium, 4d2. So it looks like zirconium. So let's check it. So krypton is 36, plus 2 is 40. Ha! So it is zirconium, so it's 40. So if you're going to lose the s's and the d's and go back to krypton, you're going to get zirconium 4 plus. Notice that zirconium 4 plus is the same as 10 4 plus, because the 10 4 plus has the added electrons. Okay? So you may be asked to do that. When you're doing the ions, especially if you're just asked what the unknown is, then good idea, count electrons. Okay? Now, isoelectronic species. We discussed isoelectronic species, and we said that they are species with the same electronic configuration. Now that you know, according to Hund's rule, etc., that you cannot have random, okay? You can't just choose randomly to throw in electrons, throw out electrons. That's not how it works. So we have to account for that as we go. All right, so that being the case, we know that we've got to have, if we have the same electron configuration, then we're going to have different charges. Okay? So, having said that, I'm rolling frantically through my notes to make sure I get the right slides listed here. Yeah, I did that. So, I want to make sure I don't leave something off. And I had them in order. And, of course, I lost the order because that would make sense to keep them in order. So, fine, whatever. Alright, so I'll wing this. Always a bad sign. So, if you'll notice, using your periodic table again, argon is your noble gas. And if you look at the argon position, Chlorine gained 1 electron, sulfur gained 2, potassium lost 1, and calcium lost 2, but they'll all go back to have this noble gas core. But they're not all the exact same species because now we have the charges associated with them. Okay, so for the isoelectronic species, the greater the nuclear charge, the larger the species is in comparison. We're going to go through what happens when you gain and lose electrons. But if you have a smaller nuclear charge, then the species gets smaller. It's kind of, flip sides of the coin. So at this point in time, we have done electron configurations. And so we're done with this chapter. However, before we do this, and I usually do this, so I'm going to add in a page real quick. We're going to play name that species. So if I give you something that has a 2- charge and it has a krypton core, so you be working on that one while I come up with another one. Oh, well, I didn't mean to do that, but okay. Oh, let me do this one. Okay, I'm working on it. Xenon core. 1, 2, 3, 4, 5, 6. Okay, so if we look at, it helps if I put the charge on there. And since you have more metals than nonmetals, you tend to have positive charges. So there's an easy way to do this, and there's a hard way to do it. Both work. Okay, the hard way is not really that hard either, but there's an easier way to do it. So if we looked at krypton, and we have a 2-, that means we have 2 extra electrons. We need to give it back. That's selenium. 2-. Okay, now, when in doubt, you can add. Krypton is 36. We have 2 extra, so we have to subtract 2, which means it's 34. So that should be selenium. Okay, so for X3, we have krypton, but we need to put 3 back. So we're going to add 3 electrons. So if you looked at it, it's going to be yttrium. But if you do the math and you use krypton is 36 plus 3 would be 39. Well, guess what? That's still yttrium. The neon here, neon, remember, is 10 electrons. And if it's 2 plus, that means we lost 2. So that's going to be 12. So who's 12? That's magnesium. 2 plus. Okay? And here, okay, this one's kind of fun. Now, if you look at it, you lost 3 electrons, and you're at the 3 Ds. So you have to have lost the 4 S's and probably another D. But in case you don't remember that, this is 54 plus 3. And then I have to add 3 back. This comes from my charge. So that would be 6. So that should be 60. So if we look at it, oh yeah, no, I screwed that one up. Because what I didn't notice was that we were in the 4Ds. So let me erase that. And let me put this back in. So there's 4F14 as well. So I forgot the 14. So we should have 74. Okay, so that should be Wolfram 3 plus. Yes, it is now. And that's why you have to be careful when you get lower down and you hit the lanthanide and the actinide. You've got to throw in the 4Fs. Okay, so that takes us to the end of this chapter. The next chapter is trends. and we're going to go through it pretty quickly because it's just a matter of knowing the trends, whether you increase, decrease, what's going on with the atoms. Okay?